Welcome back, everyone. So I've recruited my kids' whiteboard easel. So what are we going to do? Well, we're going to be looking at how to calculate a few different things for a pendulum. All right. This pendulum has a mass of 6 kilograms at the bottom on its bob. It's raised up an angle of 20 degrees, and its length is 2 meters. All right. What we're going to be looking for is the amplitude of this pendulum. So how high does it raise from here down at point B up to here at point A? Its maximum speed, which will be at point B. Its period, which means the time it takes to get from point A back to point A. And our acceleration down here at point B. All right, let's get after it. So let's start with point A, the amplitude. Well, to find the amplitude of a pendulum, when we have these basic setups here, what we're trying to do is find how high it is from here to here. All right, so let's figure that out. Well, if you go back to the other video where we talk about energy of a pendulum and all that stuff, we see that the height, or the amplitude, is the length of the pendulum minus the length of the pendulum times cosine theta. Okay, so when we lift it up, we kind of create a right triangle right here, and from here to here is this much less than the whole thing, right? So we can figure that out. So we know the length is 2 meters minus 2 meters times the cosine of 20 degrees. Make sure your calculator is in degrees, and we find that our amplitude is about 12 centimeters, right? I rounded down a scotch, but it's about 0.12 meters. Okay, cool. Point B, or part B, where we're trying to find the speed of the object down here at point B, the maximum speed. Because remember, for a pendulum, the maximum speed is at this equilibrium point. All right, so how are we going to do it? Well, this is going to be a conservation of energy type problem. All right, up here at point A, it's at a maximum gravitational potential energy. Down here, it's at a maximum kinetic energy. Since there's no energy being added into the system or taken away from the system due to friction or something, we can say that the amount of gravitational potential energy here at point A is equal to the kinetic energy down here at point B. Alrighty. By doing that, we can set up our problem. mgh equals 1/2 mv squared. Gravitational potential energy equals your kinetic energy. Well, we can say our masses cancel out. So we don't even need our 6 kilograms for this particular problem. gh equals 1/2 v squared. Do a quick algebra, we see that v equals the square root of 2gh. Right? If I multiply both sides by 2, I'll have 2gh equals v squared, square root, plug it in. All right, so let's plug our values in. V equals the square root of 2 times 9.81, or 10 meters per second squared, times our height, which we found previously, which was 0.12 meters, and we get a value of 1.54 meters per second. Right, so the speed down here at point B is that 1.54 meters per second. Awesome. So amplitude, 0.12 meters. The maximum speed, 1.54 meters per second. Alrighty, now let's calculate the period of the pendulum. Well, the equation for that is T sub P equals 2 pi times the square root of L over G. Okay, 2 times pi times the square root of, our length is 2 meters. Our G is our 9.81 meters per second squared. And we get 2.84 seconds. So it takes 2.84 seconds for us to swing from here and back. All right? That is the period of a pendulum. It doesn't have anything to do with parts A or B. It's just a thing to calculate. All right, and finally, point B, acceleration. What is the acceleration at point B? Now, remember, yeah, we call this the equilibrium position, but it's swinging. It's kind of got the bottom of a circle feel to here. So there's got to be some sort of centripetal acceleration that's going to allow it to continue in this path. So what do? Well, the acceleration is just going to be that centripetal acceleration. Horizontally, there's no forces or components of forces. Like, for example, up here, we have a vertical and horizontal component of tension, while gravity acts just vertically. Here, our tension acts straight up, gravity acts straight down. So if there's nothing horizontally, our acceleration horizontally is 0. But again, because it's swinging, we have to have that kind of centripetal acceleration. Well, what is the equation for centripetal acceleration? That's v squared over r. V is what we calculated in part B. R is the length of the string. So let's plug some values in. 1.54 meters per second. Don't forget to square it. Forgetting to square it is, not any good. Divided by your 2 meters, and we get an acceleration of 1.18 meters per second squared. All right? Hopefully that helped. Those are some very common questions you might see for a pendulum. You know, it could be something like, okay, well, what happens if the length changes or the mass of the thing changes? Right? How will that affect any of these problems? Well, we didn't use the mass at all for any of these. Yeah, mass kind of showed up here, but we canceled it out. Right? The length matters. Right? Length mattered here. It mattered here. Okay? It mattered here. So length is a very important thing for a pendulum like this. All right? I'll see you next time.